as a law about springs, that's really insufficient. Hooke's law is what's known as a restoring force. A restoring force is a force that attempts to return an object to its original shape. I'll say that again. It seems so simple, but you should probably write it down. A restoring force is a force that attempts to return an object to its original shape. So if you distort an object, if the object obeys Hooke's law, then there will be a force to try and return the object to its original shape. The simplest and probably most visual representation of this is a spring. If you have a spring and you push in on the spring, then you probably realize that if you stop pushing on the spring, there will be a force that will try to push the spring back out to its original shape. Does that make sense? If you pull out on a spring and let it go, there will be a force that will attempt to return the spring to its original shape. So a spring is a simple representation in one dimension of a restoring force. Now, to be a Hooke's law restoring force, I'm being more careful now, a Hooke's law restoring, because there are other kinds of restoring forces. To be a Hooke's law restoring force, that force must be linear. Now, what this means is the force is proportional. So if I push the spring in a distance x, the force that will push back will be equal to F. If I push the spring in a distance 2x, then the force that will return will be 2 times F. It's linear, proportional. It obeys a proportional. Now, this is what Hooke's law says, and I want to make sure you understand all the components of it, because there's really not many components here. Obviously, I have x, and it's a vector. It represents not only how much you displace the object, but what direction you displace the object. So x could be positive or negative, right? I pull the spring out, or I push the spring in. I have to define what direction is positive, and therefore I set that for x. This negative sign means that the force that is created will be in the opposite direction of the displacement. So if I push in on the spring tries to push back out. The equation is about the spring, not about me. So it explains the force that the object will apply to return to its original shape. That's why there's a negative sign here. You pull out, the spring tries to pull back in. You push in, the spring tries to push back out. But there are a lot of things that have a Hooke's law restoring relationship that aren't just springs. An inflated ball, right? It bounces because it obeys a Hooke's law restoring force. You compress it, it tries to push itself back into its original shape. That's why it bounces. The springs on your car are clear springs. Those are obvious. But there are things that are springs that are less obvious, like the catgut in a tennis racket. It's a spring. When you hit the ball, it will distort and tries to go back to its original shape. A baseball bat obeys Hooke's law. When you hit a ball, the ball compresses and the bat compresses. They both attempt to return to the original shape. Look at how much a golf club will bend upon the downswing. Again, it attempts to return back to its original shape. That snap is a way of storing the energy so that it will return to its original shape and transfer that energy to the ball. These are all things that obey a Hooke's law relationship, which is why we study them. And we study them for a number of reasons, but one of the more important reasons we'll find later. And that is because you can store energy in elastic objects. You can distort them and then save that energy for a later time. Anybody ever flick somebody with a rubber band before? You know that you can pull the rubber band and then decide when you wish to use that energy, right? Same idea. So not only do restoring forces deal with forces, but they also must have something to do with energy. So we'll come back to this, but I want to introduce the concept of what a Hooke's law restoring force is. Now, ultimately, let's say I put a block here, and the block is pushing against the spring. The spring pushing on the block is a normal force. Right? If I push this in, technically it's a normal force. We're just saying that the force from the spring will be proportional to how much you push in the spring. So that normal force on the box will be proportional to how much you push the spring in. I'm not creating a new type of force. If the spring is pushing, it's a normal force. If the spring is pulling, it's a tension. What I'm saying is that how big that force gets will be dependent on how much the object stretches or compresses. Okay? So this isn't a new force. I just know that there are going to be forces out there, normal and tension, that will obey Hooke's law. So we're going to come back to that. And to understand where we need to go, I want to introduce the word work. Now, every year when I talk about the word work, I used to go back and try to convince you that my definition for work and your definition for work aren't the same. I'm not sure that's a good way to go anymore, because first, you know more things now than you guys used to when you used to come in my room. You've taken other classes and such. But I'm also finding that more students have forgotten their IPS and physical science classes from middle school. So they don't always have the recollection they used to have. The word work in physics has a very specific meaning. And I don't want to throw that away. But to understand its meaning, you also have to understand the meaning of the word energy. And this is where my discussion in sixth period did not go particularly well. Oops, I don't want an equal sign there. I had a difficult time trying to angle in and discuss this with them. So I'm going to try a slightly different tact and change the order. I want to focus for just a minute on what you already know about the word energy. And I'm not convinced you know that many things. At least the other class convinced me that they knew very little. But again, they never saw the sun, so it's hard to know. So let me ask you some questions. Can anybody tell me anything they remember about how energy is measured in chemistry? Yes, sir?
Calories.
What's that?
Calories.
Okay, so you have a unit. Let's talk about that. That's a good place to start. My understanding is that most of the time I write these two words up there and everybody remembers that there are two different kinds of calories. And do you remember the difference between them? Go ahead.
3 calories a kilocalorie.
All right, so this is 1,000 of the little c calories, right? A kilocalorie? All right. And you're right, we tend to use that with food. Excellent. Does anybody remember the definition of the little c calorie, how it's defined? Okay, that's fine. Usually if I say it, people remember it. I very seldom have students who remember it. The thing that I think is forgotten, and maybe it's because it was never learned, and I'm having a harder and harder time figuring out which is true. Energy in chemistry is all about temperature. When you measured energy in chemistry, you put a thermometer in something and you measured its temperature. So when we talk about energy in chemistry and the transfer of energy, we use the word heat, because in chemistry, energy is transferred by heat. And you have 3 ways to transfer energy. Do you remember those 3 ways in chemistry? There's only 3. If I say one of them, you'll know the other 2. But can anybody get any of them? Go ahead.
One is like contact.
It is through contact, but there's a name for it. Do you remember the name? Yes, sir? Conduction. Conduction is contact. You can conduct heat from one object to the other by having them touch. So usually once conduction is thrown out there, the other 2 are really easy. Anybody? This side of the room is really not entering the conversation. I guess you're not part of the chat? Yes, sir? Radiation is the second one, and there's a third. Convection, that's right. So conduction, radiation, and convection. The 3 ways in which you can transfer energy from one object to another. Heat is how energy is transferred. So those are the definitions from chemistry. A calorie, therefore, is defined by heat and energy. And it has to be done so in a manner that is best used for chemistry. So a calorie is the amount of heat energy required to raise 1 gram of water 1 degree Celsius. my understanding is that you were taught this at one time, but I'm teaching chemistry now, and I still haven't said these words in that class. But a calorie is the amount of heat energy required to raise 1 gram of water 1 degree Celsius. Now, we're not going to use calories in this class the same way. We'll reference calories from time to time, but our definition of work dictates our definition of energy. For us, work isn't about heat. Work is mechanical. We are in mechanics. And so let's be clear. Mechanical means movement. That's what it means. So when we talk about work as a mechanical conversation, our definition for work must indicate movement. So work is complicated, and so I don't want to minimize it, but this is the definition of work that you must know. Now, there's verbal definitions and there's this definition. So I'm going to give you 2 verbal definitions and explain how this fits it. Are you ready? The definition I want you to know that's verbal is that work is the method by which you change an object's energy through the use of a force. Tell me I don't have to repeat that a lot. Work is the method by which you change something's energy through the use of a force.
Attention teachers.
All right, so work is the method by which you change something's energy by using a force. So that is, to me, is the best definition ever, because it tells you all the things you need to know. First, doing work requires a force. Work must be done by the use of a force. Also, you're changing something's energy. So something can increase its energy or decrease its energy. It doesn't say that you gain energy. So something's energy will be increased or decreased by the use of a force. That's all said right here, too. Doesn't look like it, but obviously the use of a force. dx means a change in position. And just one more thing, this dot means only forces that are in the direction of motion count. That's what that dot means. Now,